All right, so the three-step definition of continuity, we just kind of saw it in the warm-up. If the limit from the left equals the function value, which equals the limit from the right, well, then we know the function value is continuous. But from our experience in pre-cal and algebra 2, we have some functions that we already know about that are continuous. And so the other way you can use that three-step definition is to realize that if you know a function to be continuous at a point and you're trying to evaluate its limit, you can simply evaluate its what? If you know a function is continuous and you are asked to find its limit, then instead of struggling with trying to find the limit, just find its what? Yeah, find its y value. And you know that's going to be the same as the limit, okay? So what type of functions are we talking about that we have experience with, okay? Polynomials, right? Anything like that's like x to the first or x squared or x cubed that has like a positive integer exponent, those are all polynomials. Where are they continuous? Lines, parabolas, cubics, where are they continuous? Everywhere, right? In America, in France, on the moon. That's what we mean by everywhere, right? No, we mean this. We mean for all x. Do you see what I wrote there? For all x. You see that capsized capital A? That's a mathematical symbol, and it's legit, so feel free to use it. It means for all, okay? So polynomials are continuous for all x. If you'd rather write out the words for all, that's fine, okay? They're continuous everywhere for all x. What about sine and cosine? They're continuous where? Between 0 and 2 pi for sure. What about from like 3 pi fifths to like 1,000,000 pi 20 seconds? Yes, they're continuous also where? For all x. And when we say for all x, let me throw this in here on the back end. What does that little extra piece mean? When the numbers are real, right? For all in the set of real numbers. So in this class, we're going to be referring to real numbers all year long unless specified otherwise. We're not going to be using imaginary or anything like that. So remember, sine and cosine are the only two that are continuous everywhere. The other four trig functions have vertical asymptotes. All right? So what that means is if you're trying to find the limit of a trig function like sine or cosine, just plug it in, right? Evaluate it. And then, of course, exponentials like what we saw in the warm-up, 4 to the x, e to the x, even 1/2 to the x, which is exponential decay. Where are these functions continuous? Yeah, for all x in the set of real numbers. Yeah. Okay. Then you have functions like this. Let me throw this one in here, like g of x equals the natural log of x. This one is not, the domain is not all real numbers. You all remember what this graph looks like? If not, go look at that parent function catalog. It has a vertical asymptote on the y-axis, and it monotonically increases passing through the point 1, 0. This one can't be continuous for all real numbers, but it is continuous over its entire what? Big D word. Domain. Yeah. So this one is continuous for all x greater than 0. So that means anywhere the function exists, it's going to be continuous. So we have some that are continuous for all real numbers, and then some functions that are continuous over their domain. So again, the upshot of that is, if you're trying to evaluate the limit, just use direct substitution. Find the y value, okay? For example, example 10. Evaluate each of the following limits. All right, so we got the limit as x goes to 1 of 5th degree polynomial. Yikes, pretty intimidating. So if we had a calculator, we could put this into y1 and we can punch in like 0.99999 and 1.0001 like we did in the beginning of the lesson and see if there was some kind of y value trend there. Or we can simply do what? Do what? Yeah, plug in a 1, right? Just directly substitute a 1 in for x because polynomials are continuous everywhere. So at any and every point, the limit value is the same as the function value. So let's go ahead and plug in. We'll get 4 minus 7 plus 3 minus 1 plus 1 minus 5. And notice I wrote it directly underneath there. If you're evaluating an expression, you don't need to put an equal sign if you work straight down. Now, you'll hear me talk about different forms of answers all year long. This is an exact answer. It's not simplified, but it's exact. On any short answer or free response question, on my test, and of course the AP exam, you do not have to simplify exact answers. So you could stop right there, right? So now that you know you could stop there for a free response or short answer type question, you know you're also going to be tested in multiple choice questions as well. And if you never train for those, you're going to fall short. So know when you could stop for a free response and then keep going and train for the other type. So let's go ahead and evaluate that. Oh, I forgot my 1 there. There you go. Now you can stop. Sorry, I forgot the 1. Anyone notice that? Yeah, if I had stopped without that 1, it wouldn't have made sense, and I would have lost credit. So anyway, now if we simplify it, that's -3 plus 3 is 0, plus 0, we get -5. Okay, that would be the multiple choice answer. Now, what if it was a free response question, and you have this answer written on your paper, and it's beautifully written just like that, and then you go real hastily, and you're like, -4. Partial credit? No, you had the point, you went too far, and now you lost the point. So free response, multiple choice. Know when to stop, and then keep going so you can train for both types of questions. All right? Pretty easy. Any questions on that one? No, good question. When do we not write the limit anymore? Whenever we are evaluating, we do not write the limit. Because here's what we're saying. We're saying the limit as x goes to 1 of this is equal to this, which is equal to that. So every line is equivalent to the 1 above and below. We don't put out front here the limit as x goes to 1 equals. Why not? What is this missing? It's missing a function, right? So you don't want to put f of x there either because you never called that expression f of x. So unless you want to write that whole thing all over again, don't write it. Now, if you want, you could put the equal sign. It's not needed. The limit of this equals that. And then you'd have to put it here, which equals this. Okay, so if you work straight down evaluating an expression, you don't have to put the limit. All right? Oh, yeah, that was the wrong answer. The correct answer is -5. I was making the point of making a mistake, and I never fixed it. Yeah, good. Okay. All right, sweet, pretty easy, right? All right, letter B. Here's a way I can quiz you on the unit circle without really making it a pre-calc question. Go ahead and figure that one out. All right, we're trying to find a limit, a general limit from both sides of cosine. Where is cosine continuous? All real numbers. So the limit is the same as the function value. You evaluate a function by direct substitution. So we get a cosine of 5 pi thirds. If this were a free response question, could you stop right there at cosine of 5 pi thirds, do you think? Actually, yes. College Board and I both consider that an exact answer. It's numeric. You could stop there. You got to be careful, though, if it's like tangent of pi halves, because tangent of pi halves is undefined. But cosine of 5 pi thirds is not undefined. So on a free response, you could stop right there. That's kind of cool, right? Because if you forgot the unit circle, is it positive? Is it negative? Is it square root of 3 halves? Is it 1/2? Who cares? That's exact. You got it. But you think that would be the multiple choice answer? Absolutely not. So now we need to evaluate it for the multiple choice version of the test, which is quadrant 4, cosine's positive, so it's positive 1/2. Okay, positive 1/2. Not negative. All right, so see how you do it? Pretty easy. Train for both types of answers. Know when to stop, free response, and then keep going. All right, letter C. The limit as x goes to e of the natural log of x over 2. What is e, the number? Approximately what? Yeah, 2.7 is good. It's just smaller than 3. 2.718 if you want a 3 decimal number. It's less than pi. Is that in the domain of the natural log? Yeah, we just said that the domain of log was everything greater than 0. That is bigger than 0. So this function is going to be continuous there. So direct substitution, you plug in, working straight down, the natural log of e over 2. Is that an acceptable free response numeric answer? I just used direct substitution. Is that acceptable for a free response? Short answer? Heck yeah. Heck yes. Because it's defined. Again, if it's d and e and you leave it like that, that's no good. Like if that were the natural log of -1 over 2, that wouldn't exist. Or even the natural log of 0. But that works, okay? Would that be the multiple choice answer, though? Nope. So what is the natural log of e? That's one you should know. The natural log of 1 is what? 0, right? Past 2.10. E would be right around here. It's what? What's the natural log of e? 1. Yeah. Okay. The natural log of e is 1. So the multiple choice answer is 1/2. So you need to know this. The natural log of 1 is 0. The natural log of e is e. What do you think the natural log of e squared is? Oh, yeah. Sorry. My bad. I'm going too fast. Yeah. And then the natural log of e squared would be 2. The natural log of e cubed. 3. The natural log of e to the 4th. 4. You get the idea? In fact, the natural log of 1 is really the natural log of e to the 0, which is 0. The natural log of e is the natural log of e to the 1st, which is 1. So that was that very important property from pre-cal. Logs base e and exponential base e are inverse operations from each other. So here it is again. The natural log of e to the x is equal to x, but that's the same as e to the natural log of x. All right, very, very important. Those are inverse operations. You can compose them either way, and you always end up right back where you started with x. So that's kind of what we're doing. But numerically, natural log of 1 is 0, natural log of e is 1. So 1/2 would be the answer there. Okay? All right, so there you go. Direct substitution seems to work. If you plug into a function that's not a piecewise and you get an output, more than likely it's continuous there, and that's going to be the limit value. All right, let's look at example 6 again. If you remember from example 6, where was it? Way up here. We were trying to find the limit at 2. So we factored and divided out the x minus 2's, plugged in, and we got the value of the whole to be 2/3. But if you remember, there was this other little piece here that we talked about. The x plus 10 factor in the denominator meant that if you plugged in a negative 10, you also got a discontinuity. The function didn't exist there. And because that was a non-removable factor, that's a non-removable discontinuity, namely a vertical asymptote. So we're going to look at vertical asymptotes a little more closely now. And that brings us down here, okay? So let's say that you have a vertical asymptote. Here's a little graph off to the side at x equals c. As you approach the vertical asymptote from, let's say, the left side, there's only one of two possibilities, right? The way it's drawn right now, your y values are going down, down, down forever and ever and ever. But it could have been that as you approached it from that side, it went up forever and ever and ever, assuming that it lives on that side. Those are the only two options, right? It's not like a semi-permeable membrane where you can kind of like juke and kind of get through the dotted line, right? That's not how it works. Your y values either increase without bound or decrease without bound. Now, if I said that each of you has infinite potential, would I be putting a limit on your potential? No, I wouldn't, right? By definition, infinite potential means unlimited potential, right? And that's true, by the way. Just want to make that clear. It's true. So when we are finding limits at vertical asymptotes, especially from one side or the other, we want to say what's happening. What are the y values doing? But if we say that the limit as x approaches the vertical asymptote is, let's say, negative infinity from the left side, we're really saying two things. First and foremost, we're saying, does the limit exist? If the limit is negative infinity, does the limit exist? No. And then we're saying why? Because the y values decrease without bound. Similarly, if we take the limit from the right-hand side and the y values go up forever, we could say the limit from the right side is positive infinity, which says two things. First of all, does the limit exist? Nope. Infinity is a d and e, but we're saying why? Because the y values increase without bound, okay? So we want to try and be very, very specific when we talk about a one-sided limit at a vertical asymptote. Preferably, we put either infinity or negative infinity. All right, so here's the definition now, since we have the syntax, of the formal name of a vertical asymptote, the non-removable infinite discontinuity, also known as vertical asymptotes. And you can refer to them as VAs for now. Okay, real quickly, what makes it non-removable? Well, the same thing as the jump. If I give you a little manhole cover right here, there is no way you can move that up or down anywhere at that x value and make those graphs connect, ever. Okay? Even if they happen to go up on both sides, which sometimes they do. As they approach the vertical asymptote, they're getting closer and closer and closer to each other. But they still go up forever. So there's no way to just grab that little point. Oh, you got the idea. There's still no way to move that up or down and make it continuous. All right? So that's what makes it non-removable. So here's the definition of a vertical asymptote. If, for some function at some x value, call it c, if any one of the following four happen, you approach that x value from the right, and the y values go up to infinity, or you approach that x value from the right, and your y values go down to negative infinity. Or similarly from the other side, you approach it from the left-hand side, and your y values go up forever, or you approach it from the left-hand side, and your y values go down forever. Okay? Only one of those has to happen to have a vertical asymptote at x equals c. But what's the maximum number of those four that can happen? 2, right? Most graphs live on both sides of their vertical asymptote. But not all graphs live on both sides of their vertical asymptote. Can you give me an example of one graph that only lives on one side of its vertical asymptote? The natural log, right? Think back to a minute ago. Yeah, there you go. The natural log. It only lives on one side, okay? So that's the definition of a vertical asymptote. And then it's an if and only if, so it also works the other way around. If you know a function has a vertical asymptote at certain x value, then one of those four for sure is going to be true, possibly two of them, okay? Possibly two of them. So let's jump down to example 11. This is working off either our knowledge of parent functions, still without a calculator, or some other clever trick that I'll show you all. It says evaluate for each of the following functions. P.S. Don't use a calculator if you don't have to. Okay. P.S.S. You don't have to. Okay. All right. H of x equals the natural log of x. Bless you. You're welcome. Okay, so again, review your catalog of parent functions from my website if you're not sure. There are some at the bottom that you don't need to know yet, but all the ones from pre-cal you should know. So one way to evaluate these is just to imagine in your head or physically just really quickly sketch what the parent function or the function itself looks like. If you can visualize what the function looks like, then it's going to be pretty easy to answer the questions, right? So there it is. There's the natural log of x again. By the way, that's what log base b looks like for any log whose base is greater than 1, logarithmic growth. All right, so what is h of o? Does not exist. Good. You can only take logs of positive numbers. There's a vertical asymptote there, okay? So the function value doesn't exist. Letter B, what is the limit from the left of 0? Yeah, it doesn't exist. Because if you had the graph, you would hop on the graph to the left of 0 and start heading back to 0. Is there any graph to hop onto on the left? Nope. So this would be DNE because there's actually no graph there. You're going to find that limits can fail to exist for any number of reasons. It could be like a jump where the general limit doesn't exist because it's two different numbers from both sides. It could be like this where there's no graph at all, so the limit doesn't exist. Or it could be like this. What would be the limit from the right-hand side of 0? Yeah, this one we can actually evaluate or give some better answer. It's decreasing without bounds. So the preferred answer is going to be negative infinity. That would be the multiple choice answer that you'd have to come up with. But if this were a free response question, you could certainly put negative infinity. But guess what also works on a free response? DNE. Yeah, that works for a free response. But so would negative infinity, okay? It's the safer answer. DNE is, again, kind of a catch-all category. It's technically correct. The limit doesn't exist. But on a multiple choice for a one-sided limit, you're going to have to commit to either positive or negative infinity. And the reason you know it's negative infinity and not positive infinity is why? How do we know it's negative infinity? Well, because we know what the graph looks like, right? It's going down. What if you had a brain fart and you knew there were a vertical asymptote at 0, but you forgot what it looked like? Did it look like this or did it look like that? You know it's positive or negative infinity, but you're not sure which one. Is there a way to figure out that it is in fact negative without knowing what the graph looks like? Plug in a number. Yeah. We're approaching it from the right of 0, so what's the number to the right of 0 we could plug in? 10? 5? 5 million? How close to 0 do we need to be? We need to be as close as possible. Yeah, I wouldn't even go to 1. I wouldn't even go to 1, okay? Because remember, what's actually happening to that graph? It is negative between 0 and 1. The natural log of any number between 0 and 1 is negative, and the natural log of any number greater than 1 is positive. So in general, if you're not sure about the sign of infinity, pick a number that's like 1/10 of a unit away, 0.1, okay? So if we're approaching from the right, just plug it in and just ask yourself this question. What is the natural log of 0.1? Well, you're going to have to know then, if you don't know what the graph looks like, that the log of any number between 0 and 1 is a negative number, and the log of anything greater than 1 is positive. So that's going to be less than 0. And that's going to give you the sign of infinity. The idea being that asymptotes, vertical asymptotes, they kind of act like black holes. And the closer you are to the vertical asymptote, the faster the graph is going to be going to infinity or negative infinity. So if you're only 1/10 of a unit away from that vertical asymptote, you're already going to be sucked towards the correct infinity on the correct side of the x-axis. Okay, whereas if you plug a number that's too far away, like 2, where's 2? Right here. Natural log of 2 is a positive number. We're in the wrong spot, okay? So in general, try to go really close, like 1/10 away, all right? Now, what can be said, if anything, about the general limit as we approach 0? Does not exist. Good. So even though the limit from the left and right, neither one of them exists, we can give a better answer from the right-hand side. But because the general limit has to have the same behavior on both sides, and this one doesn't have the same behavior, that has to be D and E. You don't put negative infinity there. You have to put D and E. So what's going to typically happen is you're going to be asked to evaluate one-sided limits at vertical asymptotes. And you're going to have to know there's a vertical asymptote and commit to whether it's plus or minus. Okay? So if you know what the graph looks like, it makes it quick, fast, and easy. But there are ways to get around it, like I just showed you. Okay. Example 2, f of x equals 1 over x minus 3. What's the only value not in the domain? 3, right? So there's a discontinuity at 3. Is it a whole or a VA? It's a VA, right? Because when you plug in the 3, you get 1 over 0. So remember, from a rational function like this, non-zero over 0 always means vertical asymptote. Always. So part of it is knowing there's a vertical asymptote there, because you got non-zero over 0. All right? So that's important. We have to kind of identify the domain and what type of discontinuity it is first. So what's f of 3? Undefined. Right. You can actually write undefined if you'd like, or you can put D and E. That's a common abbreviation in this class. Even on the AP exam, you can write D and E. All right, sweet. Does the function have any shot at being continuous at 3? No way, no how, right? It's a non-removable infinite discontinuity. All right, so what now is the limit from the left of 3? If we know there's a vertical asymptote there, what is the safe free response answer? D and E. Okay, that's a safe free response answer. But that is not going to be an option on a multiple choice for a one-sided limit. But we do know then that because there's a vertical asymptote, it's going to be some type of what? Some type of infinity. Yeah, this graph will live on both sides of 3. So it's some type of infinity. How do we figure out what the sign is? Pick a number. Yeah, we're approaching 3 from the left-hand side of 3. What is the number that's just to the left of 3? 2.9. Yeah. And now plug 2.9 in right here. You get 1 over 2.9 minus 3 is negative or positive? Negative. So I got a positive over a negative, which is negative, right? So there you go. That's the answer. Negative infinity. Negative infinity. Okay. What about this guy? As you approach 3 from the right-hand side, the free response safe answer is going to be what? D and E, but that won't be a multiple choice answer. You know it's some type of infinity, so if you want to narrow it down to 2 choices, they're both going to be there, but you want better than 50-50 odds, don't you? You want 100% odds. So pick a number that's just bigger than 3, like 3.1. And what do you get when you plug in 3.1? You get positive over positive, which is positive. So the answer is just infinity. You don't have to put a big plus sign there, right? It's implied to be positive. So there's the answer. So the graph did live on both sides, but it's negative infinity from the left, positive infinity from the right. What, if anything, can be said about the general limit now? It does not exist. Good. You do not put plus or minus infinity because that's two answers. Okay, it's two different types of infinity. It's not uniform, so we have to put DNE. Nope. These you typically don't justify. Yeah, because there's really not much to justify. This is kind of like they expect you to know that. Now, there is another way to do this. The parent function for 1 over x minus 3 is 1 over x, and that's one on the catalog you need to know. So let's quickly review that. That's the one that has a vertical asymptote here and a horizontal asymptote there, and it lives in quadrant 1 and 3. It's your reciprocal function. So what would, to any function, what would it do to the graph if you replace x with x minus 3 for any function? When you replace x with x minus 3, it shifts any graph to the right 3 units. So that just moves the graph over here where your new vertical asymptote is. The horizontal asymptote stays the same, and that's what the graph looks like. So that might be a little bit faster. If you can visualize that green graph, you're like, oh, left of 3, it's negative infinity. Right of 3, it's positive infinity. Okay? What if I ask you, here's a bonus question. Same function. F of x is 1 over x minus 3. What would be the limit as x goes to 5 from the right-hand side? What would it be? Louder? 5. Nope, not 5. 1/2. Very good. How'd you get that? Plug it back in, right? Direct substitution. Don't forget the lesson we just learned. If we know a function to be continuous at a point, its limit, the general limit, which means also the left and right limit, are simply the function value. What's the only value of x where 1 over x minus 3 is not continuous? 3. And therefore, it's continuous everywhere else. So any other limit value besides 3, direct substitution works. Okay? Keep that in mind. All right, sweet. Moving on to letter G. On your mark, get set, you do. I'm going to do it too quietly, and then we'll compare answers. I hope I'm as smart as y'all and get them right as well. All right, again, look before you leap. You size up the function. You notice that there's only one value not in the domain of g of x, namely x equals -2, right? So anywhere else, this function's function value and limit value are the same because it's continuous. Is it a whole or a vertical asymptote at -2? Yeah, it's a vertical asymptote for the same reason as the previous. It's non-zero over 0 when you plug in -2. So there's a vertical asymptote. So the function value, DNE. If this were a multiple choice question, it would say either D and E, or sometimes they write non-existent. Non-existent. Either one, but D and E is shorter for y'all, okay? And that's always the answer to the function value, right? Undefined would also be another one. Now that we know there's a vertical asymptote there, if this were a free response, and sometimes these show up as just one part of a free response question, what would be the safe answer now for all 3 limits at -2, left, right, and general? D and E would be the safe answer, right? D and E, free response. D and E, free response. D and E, free response. Whew, safe, right? That's smart test taking. But we also need to be smart at math, okay? And so for the one-sided limits especially, because there's only one possibility, up or down, you're going to have to commit to some type of what answer? Positive or negative infinity. So, bless you. Again, I'll put the infinity down, and then we're approaching from the left of negative 2. We're in negative land. So what is the number that's just to the left of negative 2? Negative what? 2.1. Good. Remember, going further left. So negative 2.1. You plug it into the top, and it's positive. You plug it into the bottom, and it's who cares squared, which is positive. Ah. Okay, we're squaring it. So it's positive over positive, which is positive. Right, so that'll be the multiple choice answer. What about from the right side of negative 2? What would be a number to plug in? Just to the right of negative 2? Negative 1.9 would be super. But again, if you noticed over here, what's the last thing you're doing in the denominator? Squaring it. So it should be always what? Positive. Yeah, but it would work if you simply plugged in as well. So that'd be the multiple choice answer. Now, what could be said, if anything, about the general limit, do you think? D and E would still work, but notice the behavior on both sides is now the same. So we could actually, in the case of a general limit, even though it doesn't exist, because it exhibits the exact same behavior, we could say the general limit is also infinity. And that's saying two things again, really three things. It says, first of all, the limit doesn't exist, because infinity is not a limit, but it's because the y values are increasing without bound on which sides? Both, okay? Both sides. If it had gone down on both sides, we could say the general limit is negative infinity. That's the only time we can make that claim, all right? So over here, because it was down on one side and up on the other, this had to be D and E. We don't give two answers for a limit. We don't say plus or minus infinity. All right, so last one, take a minute and do K of X equals secant of X. I know y'all remember secant. The reciprocal of, yeah, cosine. What does the graph of secant look like? Unit circle. Can you see okay on your paper over here? Yeah? Because I can turn the back light on. Do you have an iPad? Not yet? You're getting one though soon? Okay. Do you have an iPad? Yeah, no, not wasteful. You just prefer that. I do. Okay, and you can see okay? Yeah. Okay. The nice thing about the iPads is they have their own flashlight with them. Yeah. So you kind of see what... I get it. No, that's fine.
Does beauty have to be capitalized?
How else would you do it? Lowercase. Oh, lowercase. That's fine.
They don't like the way it looks capitalized.
That's fine. Yeah. You're like an E.E. Cummings fan? Or Cummings fan? Yeah, it's a little prouder. D and E in lowercase is fine. You could do it like in cursive if you'd like. You can even put like the dots. But those common acronyms, sometimes you don't even put the dots periods because you know it's an acronym. Yeah. Okay. Cool. Yeah.
I have a question on how this could be an infinity, because I thought to have a general limit that this one also substitutes.
Oh, no, not the function value. Remember that the limit cares nothing about the bridge, which is the function value.
Okay.
The limit is only talking about the roads. So that's going back to the limit theorem way up here. We learned the limit theorem before we learned, there it is, before we learned continuity. Oops. If the limit from the left equals the limit from the right, the two roads are lining up, then the general limit exists. Yeah, okay. All right, secant. If you remember how we got the graph of secant, we sketched chala, right, the graph of cosine, high axis, low axis, high. And then the zeros became vertical asymptotes. The highs stayed high and we flipped them up. The lows stayed low and we flipped them down. Y'all remember that? Kinda. You want to sketch that? No, me neither. Okay, good. So let's just go ahead and evaluate it without sketching secant, because you don't need to know what the graph of secant looks like. Sine and cosine, yeah. So k of pi halves, is that a limit or a function value? It's asking us, k of pi halves. That's a function value, right? That's the bridge. You use direct substitution, and you get secant of pi halves. Is that an okay place to stop on a free response? You would think it is, but it's not. Why? Because it doesn't exist. So you got to be careful. It looks like cosine of pi halves or something that does exist, but it doesn't exist. Secant of pi halves is dne. So if you left it as secant of pi halves, you're going to get it wrong. Okay? You have to put dne or non-existent or undefined, any of those three. And again, if you don't like that, you could use d and e. Script like that. That's cute. All right. Okay, so the function's not continuous there, right? No way, no how? Sweet. All right, so now that we know there's a vertical asymptote there, and how do we know there's a vertical asymptote there? How do we know it's not a hole or a jump? Yeah, either you remember what the graph of all the other four trig functions, tangent, cotangent, secant, cosecant, they all have vertical asymptotes, or you remember the unit circle. Here's 0, here's pi halves, here's pi, right? The ordered pair up here is 0, 1, and secant's the reciprocal of the cosine. If cosine is 0, what's the reciprocal of 0? Good, 1 over 0. 1 over 0. If you take the number 0 just by itself and you flip it, it looks like 0. But that's not what we're doing. You could say that 0 is like 0 over 1 or 0 over 2 or 0 over 3. And if you flip that, you get 1 over 0 or 2 over 0 or 3 over 0 or whatever. So the reciprocal of 0 is dne because it's what? Some type of infinity. Okay, let's do that again. What's the reciprocal of 0? Some type of infinity. What's the reciprocal of some type of infinity? 0. Okay, there you go. They're reciprocals of each other. So now that we know there's a vertical asymptote here, the limit from the left, safe answer on a free response would be dne. In fact, that would be the same for all of them. So if you want to get that safe free response answer out of the way all the way across, general limit as well, dne. Okay, that's the safe answer because we know there's a vertical asymptote. But for one-sided limits especially, we need to know what the sign is going to be. So how would we figure out then if we know there's a vertical asymptote, knowing it's going to be some type of infinity, how do I know if it's plus or minus? Plug in a number less than pi halves. The 1/10 rule here may not be good, right? Because pi halves is like 1.57, so maybe you go 1.47 radians. That's not the best way to do that. Here's what we could do. And this is going to be kind of counterintuitive. If we think of this as the unit circle, remember 0 is here, pi halves is here. If I want to pick an angle less than pi halves, what quadrant is that? Quadrant 1, right? Because we start here and rotate that way. So an angle that's just smaller than pi halves is actually to the right of pi halves on the unit circle, right? We're not thinking of it as an x-axis anymore. And what do you know about the sign of secant and cosine in quadrant 1? It's positive everywhere in quadrant 1, right? Cosine and secant are positive. So it's going to be positive infinity from the left-hand side. I'll put a positive sign. You don't need that. And now we kind of have the way to do this. I know that there's a vertical asymptote. So from the right-hand side of pi halves, I know it's going to be some type of infinity. What's an angle greater than pi halves? Or what quadrant, I should say, in the unit circle would an angle bigger than pi halves live? Just bigger than pi halves. 2. Okay, so again, you don't go like crazy way bigger than pi halves because that's going to put you like all the way around back over here. You go just to the left, which now gives you a bigger angle, and puts you in quadrant 2. So what do you know about secant and cosine in quadrant 2? It's negative. Good, it's negative. So for the trig ones, you don't want to think about necessarily the graph unless it's sine and cosine. You want to think about the unit circle, okay? So start rotating at 0. What quadrant do you land in, and what is the sign of that trig function in that quadrant, okay? Now to verify, just to kind of show you, remember the graph of cosine looks like this. It's high, axis, low, axis, high. There's one cycle, okay? And then the way we sketched secant was this became a vertical asymptote. That was pi halves. The high stayed high, the low stayed low, and then we turned it up and we turned it down. So if you can envision that graph, you can maybe get the answers a different way. But they should be consistent with the ones we came up with, are they? Left it goes up, right it goes down. Yep, that's cool. So what now can be said about the general limit at pi halves? D and E. That would also be the multiple choice answer. Why? Because it's two different types of infinity on either side. Okay, so that's how you handle vertical asymptotes. Non-removable infinite discontinuities. Okay, let's see. We didn't finish today, but that's okay. I think we got a couple of minutes. I think I'll pick up right here tomorrow. That's pretty good, huh? Yeah, unless you want to keep going. I don't know. 13 minutes. So no, we got like 2 minutes. All right, so remember there's a worksheet for this. You don't have to turn it in, but you're practicing every day because you care, right? And you show up every day ready for a quiz, disappointed if we don't have one, excited when we do. Okay, sweet. Enjoy the rest of your Monday, Tuesday.